Yeah, g'day. So my name is Milan Clarke, and my final year project was on describing the yield of a small-scale forest in Gisborne using LiDAR. So why the focus on small-scale forests? Small woodlots will contribute to over 40% of the nation's wood supply over the next decade, and very little is known about their yields. Typically, the cost of acquisition for LiDAR is high. However, there is now free LiDAR available through the Provincial Growth Fund for regions such as Gisborne. Being accurately able to predict the yield data for small-scale forests benefits everyone in the supply chain. So I started off by getting sample plots from 3 different forestry companies, and the location of those sample plots is shown there on the figure on the left. These sample plots were used to train the models. The LiDAR was then processed in LAS tools to extract the metrics, and multiple linear regression models for mean top height, volume, basal area, and stocking were then built in RStudio. The most accurate models were chosen based on having a high R squared and a low root mean square error. The typical expected accuracy of a plotting crew in New Zealand is plus or minus 10% from the true value. So this is what I set for the desired accuracy for my models. So just a bit about the metrics extracted from the LAS tools program. So in the top right here, you can see a height percentile. This is P95. So 95% of all points fall below this height. And this can directly be related to mean top height, so the model can be more accurate. In the bottom right there shows skewness. That's the distribution of all points. And this can be related to things such as volume and basal area. All in all, a total of 34 metrics were extracted, which included canopy cover, canopy density, average height, standard deviation of heights, bicentiles, intensity, height count raster, and a height density raster. So onto the original models. This was including all of the original data. So this is the mean top height model. That red line there is ideally where all the points should be. So you can see there's somewhat of a relationship here, and their RMSE is within that desired 10% accuracy. This is the volume equation. This one was a bit weird. The model was actually predicting negative values, which obviously isn't possible in real life. This high RMSE and low R squared could be attributed to some extreme outliers. There was a large chunk of sample plots that had recorded a volume of 16,000 to 25,000 cubic meters per hectare, which obviously is just an error in the data processing. And then this is a stocking model. So basically no relationship whatsoever. Plots that had 200 stems per hectare and plots that had 800 stems per hectare were both being predicted to have 400 stems per hectare. So this is obviously unusable. So from there, I continued to build the models. So I started by removing the outliers, and this significantly increased accuracy. As you can see, the R squared increasing and the RMSE generally decreasing for all of the models. The number of variables increased for all of the models except volume. As you can see, the number of variables included in the models were relatively high. So for mean top height, there was 19, volume there was 18, and stocking there was 19. So this shows a risk or a limitation of multiple linear regression models, as there is a risk of collinearity error, and that's reflected in the number of collinear variables, which you can see in that column on the right. So in order to try to reduce the risk of collinearity error, I only included the significant variables in the next set of models, and all this really did was decrease the accuracy slightly and not really change the risk at all for collinearity error. So for the final set of models, for the combined data set, I decided to set a limit of 7 variables. This was fully to reduce that risk of collinearity error. So this is the final model for mean top height. R squared is better than the original model, and that RMSE is relatively the same. Still not really able to predict over the full range of input data though. This is the volume model, much better than the original one, no longer predicting negative values, but still that low R squared and RMSE not really within that 10%, so not the best. And then this was a stocking model again, so yeah, basically no relationship whatsoever. So from here, with that data, or those models not being up to the desired accuracy, I decided to split the data up by the 3 companies that gave me sample plots. And what I found was that using company A and B's data, it produced much more accurate models than a combined data set. And using company C's data, this produced models which were very inaccurate. The stocking models are still unusable, as you can see. And what should be noted is that the mean top height for A and B is R squared and RMSE is relatively the same. But for basal area, volume, and stocking, company A had a much higher R squared. So this just shows the accuracy difference between A and B. So for that mean top height model, you can see in that top right corner, company A and B had relatively the same R squared and RMSE, which shows its ability to follow that trend line. And then in the bottom right corner is volume for company A and B. So they had relatively the same RMSE, but company A had pretty much double the R squared of company B. And that's shown in the company's A data is better able to follow that trend line. So this shows that a large data set is not required for accurate results. It shows that a high R squared and low RMSE are both required for accurate models. And companies A's sample plots are all measured within 2 months. So this provides some consistency, likely increasing the accuracy of those models. So what can be learned from these results? The Provincial Growth Fund LiDAR can be used to create models with decent mean top height models with decent accuracy. Can create basal area and volume models that can be used to provide ballpark figures, and it cannot create accurate stocking models. This is likely due to the area-based approach used. If you're going to create stocking models, a tree-based approach should be used. However, a dense point cloud is required for that, and that's not something you're going to get from the free PGF LiDAR. Probably the key takeaway is that quality input data will directly result in quality results. So from that combined data set, this just amplified issues for MLR models, and it was impractical to create one model for the whole region with that combined data. So moving forward, how do we improve LiDAR models for small scale forestry? So a standardized approach should be used to measuring the sample plots. This includes measurement of more heights per plot, ideally all of the heights of the trees per plot, and consistency with those measurements. So ideally having the same crew measure all the sample plots. And also plots should be measured at the same time that the LiDAR is scanned. That figure up there just shows the PGF LiDAR coverage from now until 2024. Eventually the whole of New Zealand will be scanned. And I think this is a free resource that the forestry industry should be looking to tap into. Cheers.